Welcome back to Lesson 3 of our study of networks and distributed systems, based on the textbook by Jim Kouros and Keith Ross, Computer Networking, a Top-Down Approach. Let's pick up where we left off. Consider transport services that a computer network can provide in general. Here are some of the transport services provided by the Internet that you see on the screen. The Internet, specifically TCP/IP networks, makes two transport protocols available to applications, UDP and TCP, that we learned about in the first unit. When an application developer creates a new network application for the Internet, one of the first decisions that must be made is whether to use UDP or TCP. Each of these protocols offers a different set of services to the invoking applications. The TCP service includes a connection-oriented service and a reliable data transfer service. When an application invokes TCP as the transport protocol, the application receives both services from TCP. Connection-oriented service simply means that TCP has the client and the server exchange transport layer control information with each other before the application-level messages begin to flow. This so-called handshaking procedure alerts the client and the server, allowing them to prepare for an onslaught of packets. After the handshaking phase, a TCP connection is said to exist between the sockets of the two processes. That connection is a full duplex connection in that the two processes can send messages to each other over the connection at the same time. When the application finishes sending messages, it must tear down that connection. TCP also includes a congestion control mechanism, a service for the general welfare of the Internet rather than for the direct benefit of the communicating processes. The TCP congestion control mechanism throttles a sending process when the network is congested between the sender and the receiver. UDP is a bare-bones, lightweight transport protocol providing very few services. UDP is connectionless, so there is no handshaking before the two processes start to communicate. UDP provides unreliable data transfer service. That is, when a process sends a message into the UDP socket, UDP provides no guarantee that that message will ever reach the receiving process. Furthermore, messages that do arrive at the receiving process may arrive out of order. UDP does not include a congestion control mechanism, so the sending side of UDP can pump data into the network below at any rate it pleases. The actual end-to-end throughput may be less than this rate due to the limited transmission capability of the intervening links or due to congestion. At some point, we're going to see some examples of where UDP is perfectly fine for certain applications. As to security, neither TCP nor UDP provide any encryption. The data that the sending process passes into the socket is the same data that travels over the network to the destination process. So, for example, if the sending process sends a password in non-encrypted clear text into the socket, the clear text password will travel over all links between sender and receiver, potentially getting sniffed and discovered at any of the intervening links. Because privacy and other security issues have become critical for many applications, the Internet community has developed an enhancement for TCP called Secure Sockets Layer, SSL. TCP enhanced with SSL not only does everything that traditional TCP does, but also provides critical process-to-process security services, including encryption, data integrity, and endpoint authentication. We emphasize that SSL is not a third Internet Transport Protocol on the same level as TCP and UDP, but instead is an enhancement of TCP, with the enhancements being implemented in the application layer, not the transport layer. In particular, if an application wants to use the services of SSL, it needs to include SSL code on both the client and server sides of the application. SSL has its own socket API, Application Programming Interface, that is similar to the traditional TCP socket API. When an application uses SSL, the sending process passes clear text data to the SSL socket. SSL in the sending host then encrypts the data and passes the encrypted data to the TCP socket. The encrypted data travels over the internet to the TCP socket in the receiving process. The receiving socket passes the encrypted data to SSL, which decrypts the data. Finally, SSL passes the clear text data through its SSL socket to the receiving process. The Hypertext Transfer Protocol, HTTP, the web's application layer protocol, is at the heart of the web. Bear in mind, the web and internet are not synonyms. The web is a service implemented on the internet. HTTP is implemented in two programs, a client program and a server program. Remember our discussion of client-server? The client program and the server program, executing on different end systems, talk to each other by exchanging HTTP messages. HTTP defines the structure of these messages and how the client and server exchange the messages. Before explaining HTTP in detail, we should review some web terminology. A web page, also called a document, consists of objects. An object is simply a file, such as the hypertext markup language file, a JPEG image, a Java applet, or a video clip that is addressable by a single URL. Most web pages consist of a base HTML file and several referenced objects. For example, if a web page contains HTML text and 5 JPEG images, then the web page has 6 objects, the base HTML plus the 5 images. The base HTML references the other objects in the page with the object's URLs. Each URL has 2 components, a host name of the server and the object's path name. You can see the edu example here. HTTP defines how web clients request web pages from web servers and how servers transfer web pages to those clients. When a user requests a web page by either typing in the URL or clicking on a hyperlink, the browser sends HTTP request messages for the objects in the page to the server. The server receives the request and responds with HTTP response messages that contain the objects. HTTP uses TCP as the underlying transport protocol. So when somebody tells you that HTTP is the protocol of the World Wide Web, bear in mind it's not alone. The HTTP client first initiates a TCP connection with the server. Once the connection is established, the browser and the server processes access TCP through their socket interfaces. The client sends HTTP request messages into the socket interface and receives HTTP response messages from its socket interface. Similarly, the HTTP server receives request messages from its socket interface and sends response messages into its socket interface. Once the client sends a message into the socket interface, TCP is responsible for that message. Remember that HTTP and TCP are both protocols. It is HTTP's job to correctly transmit information in a form that the other side will understand. But it is not its job to make sure it makes the trip successfully. We've talked about that before. That is TCP's job. Because TCP promises reliable data transfer, the message is guaranteed to reach the destination. If it does not, then the client rightfully reports to the user that the destination is unavailable. It is important to note that the sender sends requested files to clients without storing any state information about the client. If a client asks for the same object twice in the period of a few seconds, the server does not respond by saying that it just served the object to the client. Instead, the server resends the objects as it has completely forgotten what it did earlier. Because an HTTP server maintains no information about clients, HTTP is said to be a stateless protocol. Well, that was a pretty good lesson. Let's take a break right here and take care of any assignment you may have, and when you're ready, come on back.